I don't understand.
Defense network computers. New, powerful, hooked into everything. Trusted to run it all.
Don't forget to like and subscribe.
In this project, we'll build a powerful lithium battery pack using 21 18650 cells, arranged in a 3S7P configuration. That means 3 cells in series to increase voltage, and 7 in parallel to boost capacity. That result in a compact and efficient battery with a nominal voltage of 11.1 volt, fully charged, 12.6 volt, and a massive 21,000 mAh capacity, perfect for solar setups, off-grid applications, or DIY electronics. What you get, and what you'll need to complete the build, included in the kit: 1 plastic battery enclosure, 2 cell holders, for securely mounting 21 cells, 1 3S BMS battery management system, 1 set of nickel strips, and pre-cut wire set for connecting the battery and BMS. What you need to bring: 21 × 18,650 lithium-ion cells. Same type and capacity, some Captain tape and electrical tape for insulation and safety, a spot welder for spot welding the nickel strips to the cells, a soldering iron for wiring the BMS and terminals, solder wire and flux, a multimeter for checking voltage and connections, a wire cutter, side cutter, for trimming wires and nickel strips. Important safety guidelines for your battery pack: ensure all cells in each row face the same direction, positive/negative poles as instructed in the manual. Use only cells with identical capacity, and make sure they are undamaged and not swollen. Before assembly, verify that all cell voltages are within a 50 mV range to avoid overstressing the BMS. Avoid surgical risks by never mixing different cell types. ALS: never use damaged or unvenly charged cells, only use fully insulated cells. To ensure optimal performance and safety, all contact surfaces must be perfectly clean before welding. Thoroughly clean both the cell terminals, positive and negative poles, and nickel strips using isopropyl alcohol, 90% or higher, to remove any oils, dirt, or residue. For oxidized surfaces, lightly polish the contacts with a fiberglass pen or fine grit sandpaper until they appear shiny and metallic. The contacts should be completely dry, free of dust, and show no discoloration. Before proceeding with spot welding, carefully verify these critical points to ensure a safe and functional battery pack. Cell orientation: double-check that all cells are positioned correctly according to your wiring diagram, with positive and negative terminals properly aligned in each series group. Contact surfaces: ensure all cell terminals and nickel strips are completely clean, free of oxidation, and making full contact. Any residue or gaps will compromise connection quality. For my battery pack project, I deliberately chose to make at least 3 spot welds per connection as a safety precaution. This approach provides several critical advantages for building reliable high-performance battery packs. The multiple welds create redundant connections. If one weld happens to be suboptimal, the others maintain solid electrical contact. This is particularly important for applications involving vibrations or thermal expansion. The additional welds also help distribute current flow more evenly across the contact surface, reducing the risk of localized hot spots that could lead to failure points. Before working on the actual battery pack, I conducted extensive test welds to dial in the perfect parameters. Through systematic testing, I learned how different variables affect weld quality: cell terminal coatings, nickel-plated versus bare, nickel strip thickness and composition, optimal power settings for my specific spot welder. My quality control process includes visual inspection of each weld for consistent penetration, mechanical stress testing of sample connections, resistance measurements across contacts. While this thorough approach takes more time up front, it's absolutely critical for building safe, long-lasting battery packs. The extra few minutes spent per connection pays dividends in both performance and safety over the pack's lifetime. For anyone attempting similar projects, I strongly recommend always testing on scrap materials first. Remember, in battery pack construction, there's no such thing as being too careful. Those extra spot welds and test procedures could mean the difference between a pack that lasts for years versus one that fails prematurely. Before soldering, you should check the voltage between the cell steps with the multimeter. With all cells properly spot welded, I began the precise installation of the battery management system, BMS. First, I carefully pre-tinned all solder points with flux to ensure optimal wetting and adhesion. The BMS contact tabs were bent to their required length and positioned correctly over the BMS contact. The soldering process required methodical attention. Each connection was sequentially soldered at 300 to 350 degrees Celsius using a wooden dowel to hold components firmly in position. I started with the balance leads beginning from the most negative point, followed by the main power terminals. For the final power connections, I stripped slightly more insulation than necessary from the battery cables, thoroughly tinned the exposed conductors, and then securely soldered them to their respective terminals. Every joint was visually inspected for complete solder flow and underwent gentle stress testing to verify mechanical integrity. Don't overlook the mechanical connections either. Gently test each spot-welded joint by applying slight pressure to confirm they're securely attached. Verify that all conductive surfaces are properly insulated and there's no risk of accidental contact. While checking voltages, simultaneously inspect the physical condition of all components. Run your hands lightly along the cells and connections to detect any unexpected warmth that might reveal a developing short circuit. Rough out the installation. I maintained strict attention to preventing solder bridges and ensuring all components were mounted without tension.
With all electrical connections properly installed and tested, I complete the assembly by thoroughly weatherproofing and securing the battery pack. First, I apply multiple layers of protection. For the enclosure, I use industrial-grade insulation tape, creating a vibration-resistant seal that maintains integrity even under tough conditions. This comprehensive sealing process, while meticulous, is what transforms a collection of components into a reliable, long-lasting power solution, protecting against environmental factors that could otherwise lead to corrosion or dangerous short circuits. The peace of mind knowing your battery pack is properly sealed is well worth the extra time invested. Professional tip: for extreme conditions, consider using conformal coating on PCBs and gasket material between enclosure halves for ultimate protection. This battery pack is far more than just a technical tinkering project. It marks the beginning of my personal journey towards an energy self-sufficient future.